Welcome back to our course on memory device technology for AI/ML computing. I'm your instructor, Dr. Shubhadeep. Let us try to recall what we were discussing in the last class. In the last class, we had seen that the write operation in the SRAM cell consists of two phases. In phase 1, which is the phase where storage node 1 gets activated. This happens because on the right hand side of the branch, which contains the storage node value to be 1, which is n2 is equal to 1, initiates this process because your bitline bar is pre-charged to 0, and as a result, the pass gate transistor 2 turns on. As the pass gate transistor 2 turns on, there is a write current, as I've indicated through this green arrow, which flows from the supply VDD through PU2 and PG2, thus discharging the value at N2 from 1 to 0. As the value at storage node 2 approaches 0, it results in the turning on of pull-up 1 transistor. Remember, earlier pull-up 1 transistor was off because the storage node 2, which is the input to the pull-up 1 and pull-down 1 transistor, was 1, but now it has turned closer to 0. So this results in pull-up 1 transistor getting turned on, and as a result, the second phase of write current flows in the left hand side of the branch from supply voltage and the bit line the bit line into the storage node 1, therefore charging the storage node 1 from 0 to 1. And therefore your write process happens in two stages, initiated from the node which had the storage node stored as 1, or in this case the right hand side of the branch, which had N2 or VN2 as 1, and it flips to 0. Okay, so the same concept we will look at it in a detail using the write timing diagrams. So for studying the write timing diagrams, we will again consider the example where the left hand side of the branch has a value of 0 stored in, and you would want to flip it to 1, and the right hand side of the branch has 1 and you would want to flip it to 0. As a result, you are pre-charging bitline and bitline bar appropriately into the values that you would want the internal storage nodes to flip to. Therefore, the bit line is charged to a value of 1, whereas the bit line bar is pre-charged to a value of 0. Okay, so after this, the next logical step is to turn on the pass gate transistors, and that is done by turning on the word lines, by asserting the word lines. When the word lines are enabled, as we have discussed just in the last slide, as the word lines are enabled, nothing really will happen on the left hand side of the branch, because this is very similar to the situation when we were trying to do a non-destructive read. The bit line was 1, the internal storage node was 0, and the way you had managed or managed the cell ratio, the ratio of width between PD1 and PG1, there will be not a destructive or a flipping scenario that will happen at storage node 1. This flipping scenario will happen at storage node 2 because there will be a turn on of the pass gate transistor 2. And that is what we see in the timing diagram as well. This transition in storage node 2 will happen from 1 to 0. This transition will happen because you have the turning on of the transistor and a write current which will flow from the supply into the bit line bar. And as we see that the storage node 2 starts dropping first, starts discharging first from 1 to 0. As the storage node 2 starts dropping from 1 to 0, this results in the turning on of pull up 1 transistor, and eventually even there is a transition in the storage node 1. Even storage node 1 starts charging from 0 to 1. Okay, so this is what I have indicated through the markings. N2 is flipping from 1 to 0, and this transition happens first. The next transition is initiated in storage node N1 from 0 to 1. Okay, so a couple of interesting points that might be worthwhile discussing is, since N2 discharges first from 1 to 0 and then N1 starts charging up, just notice that the crossover point is where the value of N1 and N2 are equal, will obviously happen close to 0 value. So this crossover will happen close to 0 value simply because N2 transition from 1 to 0 is initiated first. This is the first very interesting point. The second interesting point is why this is fundamentally happening. Why is N2 transitioning first from 1 to 0? The answer that we have seen in the previous class is because we have done very intelligent transistor sizing such that the pull ratio ensures that N2 moves first from 1 to 0, and also through transistor sizing in the cell ratio, we have ensured that N1 does not move first. N1 does not move first. N1 only moves when the pull up 1 transistor is sufficiently turned on. Okay, so this combination of pull ratio and cell ratio is what is responsible for a successful read operation. Okay, so with this we conclude our understanding of the write operation cycle in the SRAM cell, and we move on to the next topic. Now this is a very important topic because it talks about the stability of an SRAM cell, both in the hold operation regime and in the read operation regime. And this is the very important topic of noise margins. Now, please try to recall, we had already discussed a little bit about noise margins earlier. So how did we define noise margins? Remember, noise margins were the maximum allowable disturbance in the internal storage nodes of the SRAM cell, which does not allow the node to flip. So what is the maximum noise that you can tolerate but still maintain your previous configuration? That is the definition of noise margin. Now, since the restorative force against which this noise will try to counteract is the positive regenerative feedback, it is clear that we have to revisit the butterfly loops. Why? Because this positive regenerative feedback was a property of these hysteretic butterfly loops. So in order to understand noise margins, we have to relook at these butterfly loops. Before we do that, it is also important to note that noise analysis actually comes in 2 flavors. It is the static noise analysis and the dynamic noise analysis. What is static noise analysis? It is the analysis where we assume that there is a DC or constant noise or disturbance source with respect to time affecting either of the nodes. Now, of course, through our timing analysis in the previous section, you might have understood that this is not a realistic scenario. You would have seen that storage node N1 in case of the read cycle was going down and then coming back up. It was not a constant source, especially in the read cycle. Neither is noise a constant in with respect to time. Nonetheless, for our introductory course, what we will do is we will do the simpler form of static noise analysis, because it really helps us in making some important design decisions. So let us stick to static noise analysis for our course for the time being. Now let us revisit the butterfly loops. In the butterfly loops, we had the inverter 1 and we had the inverter 2, and they were cross coupled such that the input to the inverter 1 was the output of inverter 2 and vice versa. Also try to recall how we had plotted these butterfly loops for this cross coupled inverter, the voltage transfer characteristics for the cross coupled inverter, by doing a 180-degree shift of the characteristics of inverter 2 with respect to inverter 1, and that we were able to do because the input to inverter 1 was the output to inverter 2 and vice versa. So in this very simple example, we saw that all of the restorative feedback or the positive regenerative feedback was occurring because of the area under this hysteretic curve. Okay, so somehow we can intuitively understand that the noise margin of such a system will also depend on the area under the hysteretic curve, which I have marked here with these green dashes. Okay, so in the simplest example, we had a symmetric inverter. What is the meaning of a symmetric inverter? That the symmetric or balanced inverters, it means that the strength of the NMOS and the PMOS was the same. And that is why you were seeing that the metastable point or the transition point was roughly at VDD by 2, at half. This was because the strength of the PMOS and NMOS was the same. And therefore you got very beautiful big butterfly loops, which was giving you a lot of noise margin. Okay, so before we go into the nitty-gritty details of noise margin, let us try to form an intuitive picture in our mind that indeed it is this size of the butterfly loops which will in turn or which will ultimately decide how stable your system is. And to do that, what I have essentially done is plotted in front of you the VTC characteristics of SRAM cells, of 4 different SRAM cells, which are constructed with different inverter properties. Okay, so let us look at the SRAM characteristics shown in figure A. So in figure A, I have constructed an SRAM cell using 2 inverters which are balanced and ideal. By ideal, I mean they have very high gain. So I just described what is a balanced inverter. Balanced inverter is where the strength of the PMOS and NMOS is almost identical, and therefore the transition is happening at VDD by 2. What is the meaning of ideal? It means it has high gain. High gain means the slope of the transition is very, very sharp. Okay, so this is the meaning of high gain, that the slope of the transition is very sharp. In figure number B, we see that indeed we have a matched inverter or a ideal inverter, but the gain is very poor. Because the gain is poor, the roll off is very, very shallow or not very steep. Okay, in figure number C, we see that although we have ideal characteristics, means very high gain, very sharp roll off or very sharp transition, but this is a non-balanced inverter. They are constructed using non-balanced inverter, whereas the inverter 1, which I have indicated with the red curve, has a very strong NMOS. It has a strong NMOS. That is why the pull down effect is stronger. You see, the transition is much earlier in the x-axis, whereas the blue curve, the PMOS is stronger, and therefore the transition is much closer to 1. Okay, so this is the characteristics of SRAM cell shown in C. And then D, you have the worst of both worlds. You have a non-ideal and it is unbalanced. So now my question to you, which I would encourage you to just pause the video and think about, is which can you order these four characteristics A, B, C, and D in terms of the highest to lowest noise margin. So take a moment, think about it, and see where will the noise margin be highest, in which among them will be highest and which will be lowest, and try to rank them. So if you have done a good job at intuitively grasping the concept of noise margin, you would have intuitively thought that the size of the smallest loop is what is going to contribute to the noise margin. Why do I say that? Let's compare between figure A and figure C. It is very clear that in figure C, because of the disbalance in the inverter, one of the hysteretic loops is much larger compared to the individual loops in figure A. However, the noise margin for the other loop is what is going to be the critical deciding factor. So, in fact, therefore, we can say that the value of noise margin in C will be actually smaller than that of A. That is the first thing that we see. And of course, because if we compare between figure A and B, because we have a poor transition, poor gain and a poor transition, the size of the hysteretic loop or the area under the curve in figure B is smaller than A, and therefore we come up with roughly the ascending order of noise margin as A greater than B greater than C greater than D. So the important observation that we make is the size of the smallest loop makes all the difference, and therefore it is very important, as we can see through this figure, to make SRAM cells with balanced inverters and those containing very high gain. So this is a very important concept before that we need to discuss before we go into a formal understanding of what is the estimation of hold noise margin. So in this graph, we will see how do you estimate the hold static noise margin of a SRAM cell. So as I discussed earlier, in hold static noise margin, what you assume is that the internal storage nodes, in this case N1 and N2, are being disturbed by a constant DC source, in this case V1 and V2. Okay, so the original VTC characteristics is here shown in this particular graph using dotted lines. You see you had this very beautiful balanced inverter. However, when you start applying a constant DC source on the internal nodes of the SRAM cell, the characteristics start shifting, right? So now the stable characteristics will start shifting, as you can see from the dotted lines to the solid lines, what I am indicating over here. Okay, so this is the dotted lines, it transitions to these solid lines. Fine. Now, please try to observe, initially there were 3 intersection points between the two VTC. Let me indicate the 3 intersection points. These were the 2 stable points over here and here at 1 and 0, which was causing the memory effect, and the metastable point. So see, the dotted lines had 3 intersection points. So 2 of them are in the corners, which are the stable points that stored the memory states, while the middle one is the metastable point that could be easily disturbed by noise and flipped into either of the stable points. Okay, so once we do the static noise modeling and you use a constant voltage source that is applied to one of the storage nodes, this is effectively shifting both these VTC characteristics, and as a result you see the 3 stable points or the 3 intersection points gets transformed into just 2 intersection points. See, I have marked out the 2 intersection points. Let me clear out the graph once again and mark the 2 stable intersection points, one metastable and one stable intersection points. And as a result, now the cell is deterministically flipped only to one stable point, and in this case, that is this value A. So the answer you try and the question you try to ask is, what is the maximum value of V1 and V2 that you can apply such that the cell can tolerate this during the hold cycle, right? And that, of course, as you can imagine, is determined by the size of the maximum square. So the maximum amount of voltage that you have applied such that these three stable points gets transformed, two stable points gets transformed only to one stable point, or in other words, three crossover points get transformed only into two crossover points, is determined by this V1 and V2. Okay, so the maximum noise that the cell can operate during the hold cycle is measured by the maximum size of this nested square. This has to be a nested square that can fit into both these VTC characteristics. So I am drawing the nested square. The side of the maximum square that can be fit inside the butterfly loop ultimately determines the hold static noise margin. Okay, and this is what is the very valuable thing that we do, that we learn from doing this analysis using the VTC characteristics. Now, a practical question could be, if you have a VTC graph given to you, how do you practically extract the noise margin or the hold noise margin? And the way to do that is very simple. What you do essentially is you take the axis, the coordinate system, and you rotate as shown in the figure by 45 degrees. So you have taken the axis and just rotated it by 45 degrees. And next what you start doing is you start to calculate the maximum distance between the VTCs. This is the VTC1 and this is the VTC2, and you start calculate the difference. You start calculating VTC1 minus VTC2. So beyond this point, as you can see, this value is 0. Slowly this difference between VTC1 and VTC2 is growing, as I'm indicating. The VTC1 and VTC2 is growing, and here at this point it reaches the maximum that is given by D1. This is the maximum distance or gap between VTC1 and VTC2, and you continue it for the second loop also. Okay, and then next what you do is you extract what is D1 and D2. What is D1 and D2? The max difference between VTC1 and VTC2 once it is aligned or it is shifted by 45 degrees. And as we know, the minimum, why are we so interested in finding the D1 and D2? Because it happens to be the hypotenuse. The hypotenuse, let me just indicate it more clearly. So D1 and D2 happens to be the hypotenuse of the maximum, the size of the biggest square that can be nested inside the VTC loops or the butterfly loops. So D1 and D2 happen to be the size of the hypotenuse of the square, the maximum square which can be fit inside these VTC loops. So if D1 and D2 is the hypotenuse, the sides will be D1 divided by root 2. And therefore, the minimum of D1 by root 2 and D2 by root 2 gives you the static noise margin. Okay, so this is how you practically try to calculate what are the hold static noise margins. Okay, once we have understood how do you find out the hold noise margin, let's next move to read static noise margin. So just a thought experiment before we tell you the answer. Which of the following noise margins will be smaller? Will a hold noise margin be smaller or the read static noise margin will be smaller? So take a moment to think about it before I reveal the answer to you. So if you have been following this course very carefully, you will know that during hold operation, PU1 and PU2 or the pass gate transistors are completely switched off. So there is a small typo over here. This should be PG. However, in read operation, the pass gate transistor 1 and pass gate transistor 2 are functional. Why? Because the word lines have been turned on. And as a result, as we have also seen in our timing analysis, the internal storage nodes, the voltage on the internal storage nodes VN1 and VN2 are disturbed. And this is a diagram that we had used to calculate the cell ratio and show how the operation of non-destructive read happens. I'm just recapping it again for you. So the pull-up transistor is not operational at all. What is operational is the pass gate, the PG transistor and the PD transistor, and the read current flows from the PG transistor to the PD transistor, therefore disturbing the VN1 to 0 plus delta V dash, right? So how does this disturbance in delta V dash, which is imposed on VN1, affect your VTC characteristics? Why are we interested in the VTC characteristics? Because remember, if we can accurately find out the VTC characteristics by looking at the size of the smallest nested loop or smallest nested square which can fit inside the loop, we shall be able to calculate what is the static noise margin. And this is what we are going to do. As we can see that there is a significant distortion in the VTC characteristics when we are doing a read operation. Why is this the case? This is because, please try to recall, the PMOS part of the VTC remains unaltered, and this is what I have marked over here. So the PMOS part of inverter 1 and the PMOS part of inverter 2 is relatively unaffected. Why? Because the pull-up transistor or the PMOS is not operational during the read cycle. However, the NMOS part will get distorted. Why? Because there is a significant flow of current which happens from the NMOS. So as you can see, both for inverter 1, the NMOS is getting distorted, and even for inverter 2, the NMOS characteristics is becoming less sharper and it is getting distorted. Furthermore, it will be valuable to know that since the internal node delta VN1 never becomes a 0, it is never completely 0, it is 0 plus delta V dash. We have to also account for that in the VTC characteristics, and as shown both for inverter 1 and for inverter 2, a pure value of 0 is never achieved in the VTC characteristics, So because this delta V dash will always remain as a disturbance to the internal nodes. And this disturbance or this distortion in the VTC characteristics results in the butterfly loop to shrink. This results in the read static noise margin being significantly smaller than the whole static noise margin. Because this is because of the shrinking of the butterfly loop, the maximum size of the nested square that you can fit in these butterfly loops will also shrink. Okay. So the last thing that we will discuss today when we are talking about noise margins is what affects these noise margins in realistic circuits. So of course, as we saw, that read noise margin is much more critical. So we will focus on read noise margins. And the first thing that we notice is that as SRAM cells, please recall SRAM cells are constructed using your traditional transistor technology. And as you scale transistors, as you scale the channel length of the transistors, the goal is to go to smaller and smaller supply voltages in order to maintain, reduce power consumption. But the problem, as you can see, when you start doing that, is the SRAM cell starts showing very weird characteristics. because when you start scaling the supply voltage of the transistor, size of the butterfly loops or the size of the VTC characteristics, as you can see from this figure, also start shrinking. So when you have a supply voltage of 400 nanometers, you can see that the size of the hysteretic loop or the nested square was 105 millivolts. But when you shrink to 250 millivolts, this shrinks significantly to 45 millivolts. Okay, so near equivalent reduction in read static noise margin is seen as you do VDD scaling. Of course, this can be managed to certain extent by improving the cell ratio of the SRAM cell. Remember, the cell ratio is that which affected the delta V dash. Delta V dash was the internal disturbance caused in the storage node V1 or VN1. And because this distortion in delta V dash is what affects static noise margin, as we saw in the previous slide, by improving the cell ratio, you can somehow try to manage the read static noise margin. And this is what is indicated in this particular graph. Of course, with as we see in this figure, with reducing VDD in this graph, x-axis is supply voltage. As we see, as we are reducing VDD, the noise margins are also coming down. Why? Because the size of the hysteretic loop or the VTC characteristics or the butterfly loop is also shrinking. However, you are able to get a significant boost in the noise margins by improving the beta factor. The beta factor was the cell ratio from 2 to 3. So, one of the strategies of trying to maintain static noise margins while scaling the supply voltage of transistor could be in improving the cell ratio. But as we will see in the next class, that this is not always very possible. Why is this the case? Because the moment you start improving the cell ratio, when you start improving the cell ratio, essentially you are making your PD1 stronger. As you start making PD1 stronger, you will also have to make the pull PU1 stronger also. Why? Because you want to maintain a balanced inverter. But when you start improving PU1, the strength of PU1, write will become an issue, because in write operation, recall the strength of the pass gate transistor with respect to the pull up transistor will start getting affected. So if you try to arbitrarily increase the cell ratio, the pull ratio will start getting affected. And this is the very interesting topic of read-write conflicting requirements in an SRAM cell. We will study that and we will conclude our study of the SRAM cell. Thank you. See you in the next class.